So now you know what double star systems are and why they're important and how they've been studied in the past. But you're faced with the overwhelming task of choosing your own star system to study. Here are some factors that might make a double star system attractive to astronomers. First, if the stars appear close together to each other in the sky, they're more likely to be close together in reality. It's not a guarantee. They might be at very different distances from Earth, or they might be far enough away from Earth that their small separation in the sky translates into a large separation in reality. However, all we really have to go on is how close they appear to be, and the closer they appear to be, the more likely they are to be gravitationally bound. So we want to get them as close as possible within the limits of our telescopes. Skynet telescopes typically can resolve stars on the same image when they are as far apart or farther than 5 arc seconds apart. Closer than that, and the two stars look like a single blur, so you can't really make a good measurement. However, 5 arc seconds is kind of what we're striving for as far as a separation of stars. Another thing that you're looking for is whether the stars have moved relative to each other over the past observations that have happened. Has their position angle and separation changed between the first observation and the last observation? Because that would tend to indicate that something's happening with this system as well. Another one is that perhaps there is a solved orbit for this system, but there are some recent measurements that don't look like they fit on it. So that would make a system interesting because there's something to find out about why the recent measurements deviate or why the previous solution doesn't seem to apply. Or perhaps there's no orbital solution, but the stars seem to be moving together on the sky. And if they're moving together overall, then they're more likely to be doing that because they're gravitationally bound to each other. It's not the only reason. They might have been born in the same stellar nursery, so they're just moving together on the sky because of that. This is distinct from their motion relative to each other. The relative motion of stars as they orbit is very much smaller than their overall motion across the sky over the centuries. And then finally, perhaps there's no proof that there's a linear solution for the system, meaning a certainty that the system is not orbiting, but the stars seem to be moving differently on the sky, kind of in different directions. And if their overall motion is different, then they're probably not bound together to each other, because if they were, they would sort of be moving together as they go around. But wait, stars don't move on the sky, right? We've been making a big deal about the fact that it's the Earth's rotation that causes the stars to appear to sweep across the sky over the course of a night. In fact, stars do move in the sky, but over centuries, not over the course of a human lifetime. This is what the Big Dipper looked like in 100,000 BC. And as I play this animation, you can see that it takes on its familiar shape. And then in 100,000 AD, it will look like the big triangle dipper thing much later. Over the course of our lifetimes, it's still going to keep the familiar shape of the Big Dipper in the sky. But stars do move. Their movement is measured in units of milli-arc seconds per year. And just to remind you, an arc second is 1/60th of an arc minute. And an arc minute is 1/60th of a degree. And there are 360 degrees in a great circle of sky as you look out from the Earth. So this is a very small amount of movement per year, a milli-arc second per year. And nevertheless, over the course of centuries, and many of these stars have been being measured for centuries, that motion is detectable. So they have what's called a proper motion, and we plot it just like a vector with right ascension on the horizontal axis and declination on the vertical axis. And so if you see a proper motion of 25,28, that means 25 milli-arc seconds in right ascension, 28 milliarcseconds in declination. And so this is the primary or brighter star, and PM stands for proper motion. We can also plot the proper motion of the secondary star in this system. These two stars appear to be moving in different directions. One of them's moving this way and the other one's moving this way. So the likelihood is that they are not gravitationally bound to each other, since their overall motion in the sky is different. And we can subtract the motion of the secondary from that of the primary, get this relative proper motion vector, and figure out how big that relative proper motion vector is compared to the longer of the two proper motion vectors for the star, and we can figure out exactly how different those proper motions are. But you can see from the graph that they appear to be going in different directions. And in fact, they are. A previous InStar team proved that they were not orbiting and plotted the position of the secondary or dimmer star relative to the primary star, shown at the center of this axis, and showed that these stars had what's called a linear solution, meaning they're not gravitationally bound, they're just passing each other on the sky. And that was a very exciting result. But going in the same direction in the sky, having what's called common proper motion, doesn't guarantee that we can solve an orbit for the system. So here's another past team's star of choice. Look at how similar those proper motion vectors are in both right ascension and declination. Also, this system was only 5 arcseconds apart, so very, very close. But look at the plot of the past observations over the course of the past 100 years. Pretty difficult to defend that there's an arc appropriate for those stars. It looks like a jumbled bunch of points. That doesn't mean that they're not orbiting. It might just be too soon to tell for this system. Here's another one where you can think about whether a line would be more appropriate, and it looks like it fits pretty well, or an arc would be appropriate. Is this system orbiting and it just hasn't been observed for enough time yet? The observations represented by these plots stretch over more than 100 years. This comes from one of Richard Harshaw's examples in his wonderful learning videos. So it's hard to tell. These are 100 years of observations. If we made more observations, would it look more like a circle and we just see a teeny little part of the circle? Or would it continue to appear linear like this line? We don't know. People do plot orbits even for small amounts of observations, but they're somewhat sketchy. Here's one such orbit that's been solved and plotted. This is the primary star, and this is all the data that is in the Washington Double Star Catalog on this star to date. Even though it's been being observed for a super long time, since 1897, the stars have only moved this much relative to each other, a teeny little piece of the arc. So it seems pretty tenuous to even suggest that they might possibly be orbiting. And the researchers who proposed this orbit said that the orbit of the stars has a period of 830.37 C, where C stands for centuries. So it's going to be 100,000 years almost before we can verify whether or not these guys are going around each other. It's pretty much in the realm of non-falsifiable science, so it's kind of on the edge. But people do it. It becomes much more plausible when you can see more of the arc. So when the periods are shorter, the stars are closer. And then here's one such orbit that's been plotted, and previous InStar team reclassified this system from being a physical system, meaning a binary orbiting system, to being optical meaning not orbiting, on the basis of their measurement shown by this red X here, which is very clearly not on the solved orbit for this system. So that's another example of a very exciting result from this team who was looking at this particular star system and said, wow, that's an orbit on the basis of a small amount of data. Let's see if we agree that it's an orbit. Oh, I don't think we do agree. And so we're able to actually write a paper to reclassify that star. You might have a smaller deviation. This team looked at a star that was going around. Here's the primary shown in the middle, the brighter star in the cross. And they argued that their measurement shown in blue off of the arc of the orbit was more reliable than some of the previous measurements because of the techniques that they used. And on that basis, we're able to say that this orbit doesn't seem to be telling the whole story. No need to actually recompute an entire orbit, but it's definitely worth writing a paper about and drawing people's attention to this system as one that might not have been solved to the final precision yet. So this is your task. Think about what you would find interesting in a double star system and find 3 stars to image and make some image requests and get ready to analyze them by installing Astro ImageJ and analyzing a sample image file. Thanks for watching.